Welcome everybody to this week's edition of HoloTube with Sašo Grozdanov from Edinburgh and Ljubljana, and he is going to talk about Spectra, reconstructions, and pole skipping, and we are very happy to have you here again in HoloTube. Take it away.
Thanks very much, Matthias. Thanks to all the organizers for organizing and keeping up with this work. I mean, sort of the series of talks which came out of an original workshop. It's very nice that this is still running. Many excellent talks, so it's a pleasure to give a talk here again. So what is the title? So today I would like to talk about sort of a variety of things that have to do mainly with holographic spectra. So the title is Spectra, Reconstructions, and Pole Skipping. So what do I want to talk about? Well, I want to talk about analytic structures of correlation functions that we typically encounter in holographic theories. So what do I mean by this? So this is a typical plot of a correlation function, let's say energy momentum tensor. So it's a two-point function of energy momentum tensors in momentum space. So it's in frequency omega wave vector q space. I will often call q momentum. So this is for me momentum space. And what I mean by typical holographic theories, so in these typical theories, these two-point functions have a structure in the complex omega plane, which is a meromorphic structure. So what I mean by this, so these correlation functions at finite temperature are typically functions which have only poles, okay? So this is the typical kind of plot that I will often be showing. So what do I mean by this plot? So this is it's a plot of the analytic structure of my TT correlator. This TT correlator has some numerator B and some denominator A. And what I mean here by meromorphic is that the denominator can be factored into a product of an infinite number of zeros, i.e. so the whole correlation function has an infinite number of poles, okay? So this is then a plot of the complex structure at some fixed momentum q and fixed temperature t. If I work in dimensionless quantities, then this means that I can fix the dimensionless ratio of q over t. So the locations of the poles are basically where the denominator of the two-point function is 0. So we typically plot this kind of a complex plane, complex omega plane. When I write these kind of, fracture or Gothic script letters, these mean sort of dimensionless omega, typically normalized in units of 2 pi t. I will tell you about specifics later. But so this is a complex omega plane, and I draw a point where there's a pole of the correlation function. Okay, so these, of course, as you know, correspond to physical excitations of the system, of the spectrum, and these are the kinds of things that we'll be looking at today. Okay, so this is now, what is this? Why is this useful? Why is this interesting? Well, one point of view why this is interesting is because it tells you about the physical excitations, the actual excitations of a quantum field theory. So it's interesting from the point of view of the study of quantum field theories. Due to holography, we know that these things are dual to the spectra of black holes, i.e. the quasi-normal spectra of black holes. So if you don't like QFT, you could only be interested in quasi-normal spectra of black holes. Many people in astrophysics are, and people study quasi-normal modes. They have been studying quasi-normal modes for decades with no reference to holography or QFT. The problem is the same because we're solving the same equation. You could also, as a mathematician, just be interested in spectra of linear non-Hermitian operators. So what I mean by non-Hermitian, so the eigenvalues, you can think of these dots as eigenvalues of non-Hermitian operators. They're not real, so they lie somewhere in the complex plane. So it's an equivalent kind of question that you could ask. Or you could just be interested in zeros of algebraic or non-algebraic equations, okay? From the point of view of, this A you could take as some kind of algebraic equation or an equation in 2 variables that's not algebraic, and you could ask, well, what are all the zeros of this? So, these are all sort of equivalent problems, and they're kind of joined together under this umbrella of holography. And that's what I'll be looking at today. So so my talk will be sort of split into 3 parts. So first, I will talk about hydrodynamics in green color. So what is hydrodynamics? So the hydrodynamics is the theory of the low energy limit of the quantum field theory. So specifically, hydrodynamics here describes the behavior of the lowest pole. Okay, the lowest meaning it's the closest to the origin of 0 frequency. Okay, so hydrodynamics describes this pole here. This is a diffusive pole. I'll only mainly be looking at diffusion, but let's save this for later. And then, the rest of the spectrum is what we sometimes call the Christmas tree. So my second part of the talk will have to do with the question of whether the knowledge of just what hydrodynamic mode is doing is sufficient for reconstructing the rest, the full spectrum of quasi-normal modes in such typical holographic correlators, okay? Then I will sort of mildly switch gears, and I will go and tell you some new things about pole skipping. So why is pole skipping important? So for these types of correlators, we know, this is also now sort of old stuff already, we know that these correlation functions have an infinite set of pole skipping points. I will tell you exactly what I mean by this, but for simple purposes, it's basically where you have a pole and the zero of the correlation function at the same time. These happen at some multiples of Matsubara frequencies. So in these, simple, just thermal holographic CFTs, if this is a diffusive pole and you make your momentum Q larger and larger and larger, this pole will just travel down the imaginary axis. As it travels through, it will go through an infinite sequence of pole skipping points, which are multiples of Matsubaras. So I would like to tell you something new about these things. And then I would like to ask and just tell you the answer without telling you how to do this, because this is still unpublished. I would also like to show you how just the knowledge, or at least make a claim, that just the knowledge of these pole skipping points that are traversed by the diffusive pole is also actually sufficient for reconstructing the entire spectrum. Okay, so this will be sort of at the very end of the talk if I manage to get there. So as I already said, so we'll structure this talk into three parts. First, I'll talk about hydrodynamics in green, then about reconstruction of spectra from hydrodynamics mainly, but it doesn't have to be from hydrodynamics. This will be in red. And then in this kind of, I don't know what this is, violet, purple, I'll talk about pole skipping and what is sort of new about pole skipping and what is new about reconstruction spectra from the point of view of pole skipping. Okay. All right. So we can start. So this is a sort of a very good audience for this type of a talk. I'm pretty sure that the vast majority of you know very well what I mean by hydrodynamics. So I will go through this very fast. So as I already said, hydrodynamics is a low energy limit of certain quantum field theories, not all, but of many, especially if they're in some kind of a thermal state. So at the simplest level, what hydrodynamics is, it's an effective theory that encodes conservation laws of globally conserved operators. Okay, so for example, you can have conserved energy momentum. So you have some relativistic T mu, it's conserved. This is a word identity, which becomes the equation of motion of hydro. You can have charges, you can have normal charges, which will give you some Noether currents, or you can have higher form charges, which will give you higher form currents. What is important today is that I will be purely working at the level of classical hydrodynamics. So what I mean by this, and this is sufficient for standard holographic large N theories. What I mean by this is that T mu nu, the energy momentum tensor, can be happily expanded in an infinite series of higher and higher gradients. Okay, so what we do is we write down T mu nu in principle as an infinite series of all possible higher and higher gradient terms, where gradients are the gradients acting on the velocity field and the temperature field. If we're working with a neutral system, then I don't need any chemical potentials. Okay, so in principle, you have this infinite series, which is not known. This is not really well known at high orders. We don't really know how the number of terms grows, but this is not important here because one can assume that such a thing. And then, you plug this series expansion into the conservation law of T mu nu. You go to momentum space, i.e. you decompose your velocity and temperature in terms of Fourier modes like this. And, the result of those equations are dispersion relations. So, for everything I'll be doing today, which will be about 2-point functions, the linearized theory is enough. So I can just look at, the dispersion relations, which are only sensitive to linearized hydrodynamics. So what we know is that you can write a dispersion relation, omega as a function of Q, of the physical hydrodynamic mode as an infinite series. So it's an infinite series in powers of Q. When the coefficients, these alpha n coefficients, depend on the details of your QFT. Okay, they will depend on these lambdas here, which are the transport coefficients. And this, of course, depends on some kind of microscopic, content of your quantum field theory, which you have to compute somehow. Okay, the effective theory will not tell you this. Anyway, so the two simplest examples of such dispersion relations, and in classical hydrodynamics, above 2 dimensions, I guess the only examples of what you can get is diffusion. So if your series starts at q squared, it will start with an imaginary term. There will be a minus I, which means that the mode is purely damped. If you have sound modes, those come with a real part and an imaginary part. Okay, so at first 2 orders, the real part comes at order q, the imaginary part comes at order q squared. So you have a, this is called first order hydrodynamics. So first order, so T mu nu is expanded to first order in derivatives. So this means that the equation of motion gives you second orders, and the second orders convert into the series in q up to second order, up to q squared. Okay, good. So this is a very sort of lightning introduction and review of hydrodynamics. Now, holography, this is also a holographic sort of audience. So I will not need to say much. What is very important here is that in order to really probe specific examples of such hydrodynamic theories or of quantum field theories in which we actually have access to the spectra, holography has proven to be extremely useful. So we will use holography as a specific example of the kind of techniques and things that we would like to be doing. Okay, so in particular, we know through the holographic dictionary that in these strongly coupled large N CFTs, if one is interested in the thermal state, one can compute the spectrum of various correlation functions by studying the quasi-normal ring down of frequencies that are coming from linearized perturbations of black holes. And this is exactly the kind of picture you get. So this is why the problem of studying a QFT spectrum for the types of things I'm doing today is equivalent to studying the ring down quasi-normal frequencies of black holes. So one can ask, okay, how much do we actually know about this? So we don't know that much actually about the precise values, so alpha of dispersion relations. So for the sort of the prototypical n equals to 4 super Young-Mills example at large N and infinite coupling, all we know is the sound series computed up to q to the 4 and the diffusive series computed up to q to the 8. Okay, then things become sort of a lot more complicated mathematically, and it becomes very hard to write down closed form expressions for these coefficients. Okay, now what we have also learned in the last years, and this is by now also old story, is that it's quite useful to look at these dispersion relations and their properties from the points of view of complex spectral curves. So this is, if I go back to my original diagram, this is kind of this ellipse here. So we're kind of converting the problem into looking at zeros of algebraic or non-algebraic equations. I'll just call them algebraic equations for simplicity, okay? Because anyhow, we can truncate these things as I will be doing later. So what do I mean by this? So you can just think of this as a, finding the dispersion relations as a mathematical problem. You have some function p of x and y. You look for solutions, y as a function of x, and you have to complexify both x and y. So there's a simple example of something like a circle, x squared plus y squared minus 1 is equal to 0. You can complexify both, and then, for example, you can look at solutions. Now, of course, this is a simple example, so you can find the solution, but normally these things are way too complicated, and you cannot. So what is useful is local analysis around specific points where the spectral curve is solved. Okay, so in particular, we know by the inverse, by the implicit function theorems and things like this, if you have something called a regular point, so there's a point where p is solved, and the first derivative of p with respect to y is not 0, then you know that at such a point, an example in this case is 0, 1, then you can expand around such a point in a Taylor series. Okay, so now let's say that this is not true, it's not a regular point. But what I mean by this is that, for example, there's a point where the spectral curve is solved. So, there's an x star, y star, which gives you 0. And the first derivative of y with respect to p at this point is still 0, but the second derivative is non-zero. Then what we expect is that around such points, and in this case, there are two examples, plus, minus 1, and 0, you will have two branches of local solutions that you expand around, okay? Now, because there are two branches, they will come with powers of 1/2, so 1 over the order of the branch, and they're expanded around, 1, okay, in this case. So these are the examples, for example, around the point 1 and 0. So it's an expansion in square roots, okay? Now, what these sort of mathematical statements and theorems guarantee you is that these series are convergent at least up to the nearest critical point. Okay, so in this case, the nearest critical points are for the Taylor series here. This is it has radius of convergence 1, and the other one has radius of convergence 2. Okay, so back. So what happens when there's a critical point is that basically the two solutions cross, and then there's a question of whether you have a level crossing or a level touching solution. If there's level touching, they just kind of, the spectral curve sort of factorizes. They go through each other, and nothing happens to convergence. It's even bigger. If you have level crossing, then this, limits your convergence at that point very precisely. Okay, so as long as you have a level crossing critical point, you will limit your convergence of the series by the position where this level crossing happens. All right. Now, what does this have to do with hydrodynamics? So, in brief, basically, when one solves these hydrodynamic problems, when you're looking for the modes of the problem, you solve the same kind of equation. It's some p as a function of momentum vector squared and omega, and you're looking for solutions. So for example, in first order hydro, the solutions to which I showed you earlier, it's just diffusion, standard diffusion and sound. This is what this looks like. So there's a factorization between the diffusive part and the sound part. And actually the diffusive part comes to the power of 2 because I'm working in 3+1 dimensions, okay? Now, if I state what I just told you slightly more formally, there's something called the Puiseux theorem, which tells you that now around a critical point being defined in this way, so that, the point is a solution to the equation, and then my first derivative with respect to omega, which is, I'm solving for omega. So the first derivative is 0, and then some p derivative is non-zero. So this is a critical point of order p. It tells you that, the Puiseux theorem tells you that there are p branches of solutions. Typically, I mean, there can be special cases where, you have some simplifications, but in general, in these kinds of cases that I'll be looking at, you have p branches of solutions around such a critical point, okay? And convergence is guaranteed up to the next level crossing critical point. And you could also think of this as a branch point in the space of momentum. So we'll deal with this later. So basically, hydrodynamic series have a finite radius of convergence, which is determined by these nearest level crossing collisions. Okay, so this is a kind of a typical picture that we like to draw to see where this happens. All right, so what is important for purposes of my talk today is that yes, there is hydro, they are Puiseux series, and they are convergent. And one can, for example, again, for n equals to 4 super Young mills, for shear and sound, one can compute what this radius of convergence is. This is, for example, the calculation for n equals to 4 super Young mills with leading order correction in the 12th coupling. That's, again, as much as we know about these things. We don't know any more about this theory. We don't know what the subleading corrections, for example, in the inverse 12th coupling are. We also don't know, what to do with finite n corrections to these things. Is this even a well-defined question? Given long time tails, things like this are, sort of work in progress by various people. So what is important here for me is that for all these theories that I'll be looking at, you have a hydro pole. This has a series expansion. And if you go to now plot the complex analytic structure of the dispersion relation, omega as a function of q squared. So this is now the complex q squared plane. There's a holomorphic disk. All right. So, it's convergent in Q up to something where something terrible happens to it, i.e. when it collides with something. So these collisions are reflected in branch points that lie, so the nearest branch points lie on the circle of, on the disk, on the boundary of the disk of convergence, okay? And they limit convergence, and then, things happen. So this is, for example, it's not a cartoon, this is an actual calculation of what the analytic structure of the diffusive mode looks like in n equals to 4 super Young mills. All right. Okay, good. So this is the sort of the statement that I want you to get from this part. So now I would like to talk about reconstruction. All right. So there's a question. If I know everything about this hydrodynamic mode, i.e., I know what it's doing in this disk of convergence in this green region, is this enough for me to figure out what the dispersion relations are of every single mode in the rest of the spectrum? All right. So this is it's an equivalent question that Ben Withers asked in 2019, and he looked at an example of this in a holographic example, and he showed using PADE how you can do this for one node. Okay, this is a specific example. So I would now like to look at these kinds of neutral CFTs and make a statement of whether this is possible for every single node, all right, for the entire Christmas tree. And also, in order to do this, what we tried to do was come up with some practical algorithm that could in principle work and sort of develop, how you actually do this. Okay, so all right, so that's what I want to tell you about now. And this is all of this is from a paper with my student Timothée Lemut, and it's from a paper published quite recently in JHAB. Okay, so all right, so let me be slightly more formal. So let me go again through these statements of Puiseux theorem, which I'll be using heavily, and one other theorem called the Darboux theorem. All right. So what is the Puiseux theorem? So imagine you have a critical point. All right. So around the critical point of order P, which I defined earlier, and this is again the same definition. So I have some, function of x and y, and this function, let's say at 0, 0, because I'll be, for concreteness, looking at Hydra modes. So you can think of, y as omega and x as q squared. So at 0, 0, this is solved, okay? i.e. I have a gapless mode. Now, the derivative with respect to y at this point is 0, and only pth derivative with respect to y is non-zero, right? So this I would call a critical point of order 2. Now, what one expects is that around this point, there will be p branches of series solutions. Okay, so what I mean more precisely, there's y, some kind of as a function of x. Now there are p branches, so there's an index j that runs from 1 to p, and it's a series with some coefficients, and the expansion parameter is x to the power of k over mj. Okay, now so this is solid. This is what happens. This is a general theorem. Now, what is interesting is that if mj is greater than 1, then we necessarily have a family of mj solutions such that essentially their phases, okay, lie on a circle, right? So this is for, for p is equal to 2, where mj is also 2, so that it's an expansion in square roots. This immediately implies that you will, like with sound mode, you will get these plus minus solutions, okay? This could also, be 3 or 4, and then you would have 3 branches where these phases arranged, equidistantly along a circle. So the point is, if you have this mj, so right, mj is telling you what is the expansion parameter essentially, and you can find all these mjs and ak's, various methods, for example, from the Newton polygon. I won't be using this here, but you can learn how to do this from our papers. Then there, as I said, there's sort of a sub branch of solutions labeled by L, which goes from 0 to mj minus 1. Okay. Now, for simplest examples, like everything that I'll be doing here, like also for sound, this is sort of fairly easy. So P is equal to 2, and mj, so mj is this 2 as well, right? So there's an expansion in square roots. Now this immediately implies that there are 2 branches. So mj is 2, mj 2 minus 1 is 1. So there, there's a branch labeled by L is equal to 0 and a branch labeled by L is equal to 1. And these are the, with the phases arranged sort of at, plus and minus along the circle. And you get 2 branches, and this tells you immediately the structure of the sound mode, i.e. it tells you that the real part comes with plus minus and the imaginary parts are always the same, okay? So this is a sort of a fancier, more generalized way of arriving at what I already told you. Okay, good. Now,
Sašo, can I ask a question here? Is Richard?
Yes, is that Richard? Hey, yes,
yeah.
please.
Is there a relation between P and MJ in general, or they're just could be completely independent?
Yeah, they can be independent. This depends on the nature of the critical point. You can come up with all sorts of examples.
Okay.
Yeah, there can be factorization. So, each one. So, for example, MJ will be, yeah, we have examples in the appendix of this complex life where MJ is not equal to P. So we show an example of such a thing. Yeah.
Okay, thanks.
Great. Okay, so the second statement is what is called the Darboux theorem. So this is sort of less well-known thing. So what is the Darboux theorem? Okay, so now imagine, right? So I have my hydrodynamic function. It's, you know, it's an expansion, infinite series expansion in this holomorphic disk. I will now write it like this. So I have some f of z. It's an infinite series with some coefficients. So what we know, for example, in the simplest case, this converges up to a critical point, all right? So something happens to it. So let's look at an example. So these are the standard Darboux examples. So imagine that you have a single critical point here at Z1. So this will limit the convergence, okay? So what Darboux theorem does is it expands the function f of z around the singularity, okay? Around this critical point. So let's say you write down an ansatz. So there's an ansatz of a critical point. It's a little bit, the notation is maybe not perfect, but this is usually how it's done with Darboux. So there's a parameter nu, and in our language, this will be -1 over p. So for all examples, this will be -1/2. Anyway, so you write f of z as z minus z1, okay, to some power. Now this power is not an integer, so it means that, you know, the function is non-analytic at that point. Again, for our cases, this is 1/2, so minus nu is 1/2. You know, it goes as a square root. At that point, it goes as a square root because actually two quasi-normal modes collide there, and then they level cross. So this is, okay, the general ansatz, and this can be multiplied by some regular function at z is equal to z1, okay? So this is r plus some function that is regular from the start, okay? So this is the most general thing you can do. You can write it in this way. And what the Darboux theorem tells you is, at first, how to compute nu, okay? So you can compute nu from the high order asymptotics of the series an in an, okay? So basically, this is, it's a little bit like these tests for convergence, where, you know, you need to know the high coefficients in order to compute the radius of convergence. So this is a sort of a fancier, smarter way of reshuffling this kind of ratio test that will tell you what is the order of the singularity, okay? What is the order of the critical point? So there's a relation, it's important for me to stress this. So this is a relation between nu, the position of the critical point, Z1, and the coefficients, the high asymptotic coefficients of the hydro series, okay? So, you know, with some ratio, Z1 is very important, where the collision happens, where the critical point is, and then you take the limit n to infinity, and you can show very easily that you know, this will give you nu, the order, okay? Now, okay, so you can find this from the Darboux theorem, but what is very nice is you can also find all the coefficients in the expansion of Rz, and then eventually also Q, okay? So now imagine that you write Rz as a regular series like this, Rm z minus z1 to m, so this is the Taylor series, everything is nice and regular. Then you can also use these kinds of, you know, more complicated reshufflings of things, of the coefficients, and you can express each Rm as the kind of a recursive procedure, okay? So this is some, I don't know what to say about this. It's just some algebraic expression that includes some factorials. It depends on the coefficients of the original series. These are the Pochhammers. And basically, you know, you go sort of recursively. So what I mean by this, so Rm, let's say for some specific m, will depend on the R case going from 0 to m minus 1, okay? So this is a recursive procedure. So you basically use this high asymptotic coefficients to compute one, then you compute the next one, and the next one, and the next one, okay? And in principle, let's say you know all the coefficients, and you know that this is a series with only one critical point obstructing its convergence, then you can do this, okay? Now, what is also actually important here is that the realization that you cannot do the whole reconstruction. You see, there's a single equation here that involves both nu and z1, okay? So you need to know either one or the other, okay? So this is it's a potential problem. So we'll resolve this. I'll show you how this is resolved. But for now, I think it's important to know, because what we would like to do is reconstruct everything just purely out of an, okay? And as this theorem stands, this is not possible, all right? because you have a single equation for two pieces of information that you need. And then, okay, if you have that, so, you could reasonably assume that nu is -1/2. That's okay. And then you can get Z1, for example, that you can do. And then you get the remaining R's this way. Okay, now, so how do you get Q? So that's also quite simple. So what you do is you just take your function, you multiply it by Z minus Z1 square root of that. So, now QZ will know, or sort of rather, square root of Z minus Z1 times Q will no longer be a regular function. So you use Darboux theorem on this redefined function. Okay, it's not very complicated. You just kind of trick it in a way that it becomes the leading non-regularity of some newly defined function, and you just use the same thing. So you extract all the QMs. Okay, so QMs are the series expansion coefficients of Q. All right, in exactly analogous way as RMs are the series expansion coefficients of RZ. Okay. Right, so this you can do. So one problem that appears is that, well, you don't necessarily have only one critical point. Actually, when I showed you the specific calculation for n equals to 4 Young Mills, there were two, right? So these are actually two critical points that appear at complex conjugated locations. And, in these many holographic examples, this is what you'll find. So, for example, you can have an example like this, where you'll have two conjugated critical points at the boundary. Other things could also happen. In general, you could, maybe not in holographic Hydra examples, but for some other functions, you could also have two critical points at generic points, Z1, Z2. And then what actually turns out to be very useful is to also understand this Darboux ansatz business when you have two critical points, let's say Z1, Z2, but there's really only Z1 that's limiting convergence, but Z2 is very close to it. I will explain why this is important later. And then you can have some generic example where you have, J critical points on the boundary of the disk or near the boundary of the disk. So, what we did, for example, in this paper, we generalized this Darboux story for any such case. Okay, that's the one thing we did. And then the second problem that we had to solve was to figure out exactly this. So how do you get everything out of only the coefficient an, because of this problem that I explained here? So actually, we didn't need to do anything because this was already resolved in 1980 by Hunter and Guerrieri. There's a very beautiful paper by these two, mathematicians, I suppose, where they figured out how to do this. So there's a sort of a trick. You can define some polynomials, essentially. So this is the notation is not very revealing, but you can define some kind of polynomials recursively. So let's call x0n an. Okay, these are our original coefficients. And then you recursively define xn with another, this is not the power, it's an index, m+1. So you recursively define them in this way. Okay, they did it. It's very nice. You can show that asymptotically, as you increase n, how this will behave. Okay, so n is the order, you can think of it, order in the gradient expansion, and m is an order in this iterative procedure of Hunter and Guerrieri. So what you can prove quite easily, actually, is the following thing. So let's say you start with two equations. So you can first solve x1 n. N is let's say the last order of the coefficient you know. You can solve two equations. Now you have two equations, actually. So you can solve two very simple equations for both Z1 and nu, okay? And then you iterate. So now you iterate over M, and you basically use these solutions as a seed, and you iterate over M, and eventually this will converge, actually, to Z1 and nu, okay? So it's a way for you to find both Z1 and nu. So nu is, our square root, and Z1 is the location of the critical point from only knowing an, the coefficients, okay? So this was shown in their paper. Then they have a comment, well, this can also be done for the coefficients of the series for all of these R's and Q's. They don't tell you how, but okay, we worked it out. You define some more stuff. These are now Y's, okay? So Y0, Ln, now there are two indices, are still the original coefficients, and then we define these kinds of even more complicated recursive polynomial equations. We prove how they behave as a large order in the gradient expansion, and we find an expression how from this from these polynomials you reconstruct RL. Okay, so basically you can get everything out in this sort of Hunter-Guerrieri way, and we show how to do this explicitly, and then also get Q. All right. So what we also did in this paper was to extend this algorithm. It becomes more and more complicated because, again, you know, I was only showing you so far what happens when you have one critical point, which is not actually what we want. So we also extended this to algorithms, this Hunter-Guerrieri style algorithm for any number of critical points. Okay. Now, another thing I should say is that this algorithm is also very useful when you actually don't know all of the coefficients. Now, of course, you know, if you know all the coefficients, then you can very happily take the limit. This is very nice when you look at the toy example. So if you have something like, you know, this linear axion model at the self-dual point, it's very nice. You can just do it. You take a limit. It's very nice, binomials. But in general, you cannot do this because, you know, as I told you, analytically, we know, say, only 4 terms in this series. Numerically, we can compute some number, let's call it n. And then you would like to know how to do this. So, you know, this algorithm also works for that. Okay. Sort of, you know, because we worked out how the error in the expression behaves, you have actually some control over these errors. Okay. So we have this, we developed it. And now what is the claim? So the claim is that in these kinds of theories that I'm talking about, you can actually systematically reconstruct all modes, all modes that are connected in some way to the hydro mode via level crossing, by doing essentially an exploration, a detective-like exploration of this complex Riemann surface, okay? And then connecting these modes together. So to be precise, so how do you do this, okay? So I should also say that I think that morally, this is equivalent to what is done in position space, and people do resurgence, like, you know, Borel resummations and things like this. So what is nice about, you know, correlation functions in momentum space is that everything converges. So you don't have to worry about Borel or Pade or these kinds of things necessarily. Okay. So what do you do? Okay. So you start with this series. So this is what you know, right? So you know this, the expansion around the series around 0. Then, and this is the series. Okay. Then you use the Darboux theorem, and you figure out what is going on at the edge of convergence. Okay. So you go through this Darboux procedure and you figure out how many critical points you have. You figure out where they are, what their order is, and what they're doing and where they are. Okay. And then you can still use this Darboux to even re-expand the function around the critical point. Okay. So you've now re-expanded the function. It's drawn here, so let me go down. So now, you know, from the starting point of coefficients an, then you re-expand the function using Darboux, well, there are other methods to try to do this, but, you know, I will talk about this later. For now, I'm just talking about Darboux because we have sort of a new systematic way of doing this. So you expand around this point. Okay, so this is now a series like this. It's a series in square roots. Now you know immediately by Puiseux theorem that this will also have a brother. So it has a second branch, because actually, you know, the reason why you have a critical point there is because 2 things collided. So there's also a second branch. It's a second branch of the Riemann surface. And, you know, just straightforwardly from the Puiseux theorem, you figure out what the coefficients are of the second branch. So the second branch is the second quasi-normal mode. Okay. So if I start from the hydro mode, so this hydro mode eventually collides with the first gapped quasi-normal mode here. And the second branch of the Puiseux series is the dispersion relation of the second quasi-normal mode expanded around the critical point. Okay, so you've recovered it, so you get it. Then you have to do more complex analysis again. You know, then you have a series expansion around a point. Then you do analytic continuations to go outside. And what you do then, for example, is, you know, you repeat the procedure. So, you know, you find again what is the radius of convergence of that series. These are now series around, you know, expanded not around 0, 0, but around somewhere else. And, you know, you can just recursively use Darboux. And you know, in principle, the claim is that as long as all of these quasi-normal modes are related via some kind of, paths that have a collision, which is a level crossing collision, so they have a non-trivial monodromy, then you will be able to calculate all of them out. Okay, in principle, you can get everything out from only knowing the coefficient of the hydro series. All right, now I would like to show you. So this is all very nice. I mean, you can, I think it's by itself, it's a nice claim. It means that, all of these modes are, intimately related. They all know everything about every other mode. So it's, it's a bit like going from infrared to ultraviolet, although of course, the infrared has an infinite number of coefficients. So, the statement is really that this infinite number of coefficients somehow secretly contains all the knowledge about everything, all the way up to the ultraviolet. I think it's still non-trivial. I think it's a highly non-trivial statement because, it doesn't have to be like this. You can also cook up examples where this isn't the case. But in these, simple holographic models that we all love, like momentum diffusion, let's say, of M2 branes. So what do I mean by M2 branes? Maybe for those of you who didn't read original papers by Herzog and people. So this is just ADS4 Schwarzschild black brane with nothing but fluctuating gravity. Okay, this is pure gravity in ADS4 Schwarzschild. So in the transverse channel, I keep doing this. In the transverse channel, this is the diffusive pole. So there's a diffusive pole, and it has some series, and we were able to find numerically the number of coefficients that was 300. Okay, we could do more, but anyway, just to see how this works, we found 300 coefficients. So what do you do then? So there's a sort of a kind of a stupid, non-rigorous way of looking for the number of critical points, actually. So of course, if you had the whole series, then all you know is that the series diverges at some point. But if you have a finite number of series, what you can do, and this is actually practically very useful, you can just plot the function at the disk of convergence. You find the radius of convergence from the coefficients, and you look at the function. What is it doing? So you look at the function and its derivative, and actually it tells you in a non-rigorous way, it indicates to you at least, that it's very clear that, as you vary the phase around the disk, that there are two complex conjugated critical points. And actually, this is exactly what is really also happening. So, it gives you an indication that you should be using the algorithm with two critical points that are complex conjugated. This was this option B that I had before. And then you just do it. You use Puiseux. So you go through this procedure. It's, algebraically a nightmare, but it's all just algebra. And what we show is that with this algorithm, we get 12 series coefficients of the second mode expanded around Z1. Okay, this is how well this works. So from 300 initial coefficients, we get 12. So what is happening strictly here, right? So we start with a series here, and then we use this continuation to find the series around Z1. Okay, this is what's going on. So then we find this Z1. Now, for example, you can see that this Z1, the series around Z1 of the second mode, doesn't actually extend to the origin. So this means that you can't just, put in Q is equal to 0 and evaluate the gap because it doesn't converge. So what you can do now is actually use, any analytic continuation. But what is important, use an analytic continuation within the same sheet and, within the same Riemann sheet, because you use this Darboux to go to the second sheet, then you're within the same sheet. And then Padé is extremely good. So you can just use Padé. You don't have to worry about anything. It just works. And you can find the gap. So from this result, we were able to calculate the gap of the first quasi-normal mode to this level of precision. Okay, so this is the actual value calculated from the spectral curve. And this is the numerically reconstructed value. It's not too bad. I mean, it's not perfect, but I'm happy with this. So then the question is, can you go further? Okay, can you go further? Now, it's not so great, right? So the problem is that now we have only 12 coefficients of this sort of yellow series around Z1. And it's quite hard with 12 coefficients to go to the next level, to go to the, to quasi-normal mode number 3 and reconstruct the next one. So what we do, just to show as proof of principle that this works, that the reconstruction doesn't stop here, is we just recompute the coefficients. So, for kind of precision, we just did it for 300. So we recomputed 300 coefficients, and then we repeated the analysis. So what is now interesting, if you just, blindly, idiotically look at the behavior of the function now I'm looking at the dispersion relation of this first gapped quasi-normal mode expanded around Z1. What you see is actually quite interesting. So you see two potential singularities. So what is actually going on, right? So you see, so there's a critical point, which is the complex conjugate of Z1. So there's Z1 star, which is here, and there's Z2 here. So actually what is interesting, what happens in this case, this is case specific, the Z1 star is actually closer than Z2. So you could worry that, well, actually, formally speaking, now I don't have access to Z2. But this isn't true, actually, because you can use the Darboux ansatz. So you can, this is this case. So you have, no, sorry, it's this case. So you have one critical point, which is at the boundary. And then you have one other critical point, which is slightly further away. And you're actually interested in re-expanding the function there. So you can actually, by the procedure that we developed, you can just do this, okay? So you put in a different ansatz that has two nearby critical points, and you go through this procedure. And what is interesting, again, from 300 coefficients, we get 12 coefficients of the next mode, okay? So we've gone to, I don't know, level 2 now. So you can get them. And now this is, this is now the second gapped mode expanded around Z2, and we have 12 reliable coefficients. Again, you do some kind of analytic continuation within the same sheet, and you can calculate the gap. So from this data, this is now our calculated gap. So the value of the second quasi-normal mode at 0 momentum, and you can compare it to the to the numerically computed thing from the full spectral curve, and they match pretty well. So this worked. So you then just continue. So but what you do then is, well, essentially you explore. So you have to sort of blindly explore this multi-sheeted Riemann surface, and you go from point to point, you reconstruct, and you can just sort of, I have this symbol here, you kind of like a detective find everything that's happening, okay? Unless there's some horrible obstruction, I don't know, unless one of these series, which I don't believe is the case, would have the property that it would not be analytically extendable. There are these, I don't know, things called lacunary series, which are not analytically extendable, but I don't think that in these holographic cases, and we're developing more and more sort of insight into these functions through these methods of point polynomials and things like this to see that this is really not the case, okay? We have these well-behaved things and we can just reconstruct everything out of it, okay? Good. So what is maybe interesting is this, you could just use Padé, okay? You don't have to go through this whole Darboux business. You can just try Padé. So what we did was also to compare with Padé with the same number of coefficients. So this is also the method that Withers used in 2019. So I think it's actually quite interesting to compare them. And for some things, Darboux is much better. And for some things, Padé is much better. So I think it's good to be aware of this, so that you can effectively use numerical methods, because numerical methods are, at least to the level I think that we're using them, often more of a art than science. You kind of just do something and you try and it works or it doesn't. But I guess complex analysis is kind enough that as long as it works, then it's correct. That's at least we can, the analytic structures are nice enough so that things are usually okay. So, okay, so what is the problem? So actually, the best thing about Darboux is that it gives you the critical point, okay? With this algorithm that we developed, or that's like the Hunter-Guerrieri thing, what you get amazingly well is the location of Z1, okay? It's the position of the critical point. So if you use it, in this case, you get it to 18 significant figures. Now, and this is the main problem of Padé, because with Padé, you look at singularities and you know that the actual singularity is some kind of an accumulation point of things not going so well with your Padé approximant. So in this case, with Padé, we could not get it to be better than 3 significant figures, okay? So if you really have only the coefficients, then I think Darboux is really superior in this case, just because it gives you a much better approximation to the location of the critical point, okay? Then, for example, Padé is really good after that to use it within the same sheet, because if you use Padé within the same sheet, then you don't have to worry about the critical point. You just use Padé, you evaluate it at the origin of the complex plane, it will give you the gap. So Padé works very well. For example, it will give you something like 17 significant figures. Now, what I find really interesting is, let's say you actually do know for some reason where the critical point is. Okay, let's say you have some independent way of finding out where the critical point is, then actually Padé is absolutely amazing. So if you use our example with the coefficients that we have, and you sort of calculate independently, I don't know, someone gives you Z1, and then you use it, then actually this omega 1 of 0, the gap can be computed actually to 26 significant figures, which is amazing. And what we're able to get is 80 coefficients as opposed to 12. Okay, so it's kind of, I think it's an interesting situation. So the unsurprising conclusion is that, well, you should try different methods. So yeah, if you know the critical point, then Padé is great. But the problem is that with Padé, the determination of the critical point is really pure. So usually then that kind of precludes you from being really good at subsequent steps. So that's sort of my impression of the methods for now. Is this useful? Conceptually, I think it's very useful because it really teaches us that these modes are all connected together, at least in these models. Okay. Practically, is it useful? I don't know, not really, because so far the level of decrease of the order of magnitude of how many coefficients you get, of how many coefficients you get at each next level of reconstruction is about an order of magnitude. So maybe this can be improved. We're looking at this, but it's not really clear. So, okay, so I am sort of maybe running out of time. I don't know, Matthias, how much time do I have?
You have at least 5 more or 10 more minutes.
Okay, this section is actually very short. So I just wanted to tell you some new things about this, because I would like to go further. Okay, I would like to know whether actually, because pole skipping points are in principle much easier to calculate because they're all coming in principle from algebraic manipulations around the horizon. Now, if you've never seen this, then you don't know what I'm talking about. So what is pole skipping? Let me just try to go through this briefly. It's, at first, at least the way we found it, it was some relation between hydrodynamics and quantum chaos. So, in these holographic models, what is quantum chaos? Well, we believe that these theories are extremely chaotic, actually maximally chaotic, in the sense that they have maximally growing out-of-time order correlators. So they have two pieces of information that quantify the growth of this OTOC. One is the quantum Lyapunov exponent, which for all these cases that we're looking at is 2 pi times the temperature. It's the maximal one saturating the MSS bound. And then the butterfly velocity of this chaotic spread is non-trivial. Okay. Now, what we were able to see from sort of analysis of hydrodynamics or shock waves and various things that we were doing is that actually this knowledge of quantum chaos is encoded secretly in the behavior of the hydrodynamic mode. Okay. So what we were able to show is that this dispersion relation, let's say everything about this dispersion relation passes through some kind of a magical point. And this magical point, if you look at sound mode, will be for frequencies at the Matsubara frequency times I, so positive imaginary axis. And this will happen at imaginary momentum Q. And actually this imaginary momentum Q, where this happens, is equal to I times lambda L over VB. So this allows you to compute the butterfly velocity just from the hydro mode. Now, what is important about these points, so these types of points, they're now called pole skipping points, have essentially, so if you have the pole, what happens is that at these special points, the residue of the correlation function vanishes. In other words, basically the function is 0 over 0 at that point. So the whole Green's function is 0 over 0 at that point. So actually, the value of the Green's function is still regular, but the value is determined by the angle of approach to the point. Okay, so there's some ambiguity in the value of Green's function coming from the limit in the omega Q space that you take. The details are not important. What is important is that there's actually an infinite number of such points. Okay, so these pole skipping points, now we know, occur in all these holographic correlators at integer multiples of negative Matsubara frequencies. Okay, so for omega n at some qn being equal to minus 2 pi tin, for n being a positive, well, typically an integer larger than, starting with -1. So -1 is the smallest it can be in the sound channel. But just think of it as integer multiples. At these things, there's always some qn. Actually, there's an infinite number of these qn's where you have a 0 over 0, okay? Very simple. So what do I want to tell you about this? So actually, it so happens that if you look at diffusion in purely thermal theories with no other scales, then this diffusion, like I showed you before, if you just increase Q, will happily just go down the imaginary axis. So as it goes down the imaginary axis, of course, it's only well described here by this series, but then after that, it's some analytic, unique analytic continuation of this series. So this mode will go through the infinite sequence of pole skipping points. So there's a very nice picture from Blake, Davis, and Weg, this paper, where they showed the method, the most efficient method for finding these, pole skipping frequencies at higher Matsubaras. So you should disregard this line. You should just look at the dots. So you can see that the dots are the actual positions of the diffusive dispersion relation, and it goes through the pole skipping points along some curve. So what I was able to actually see, which I was quite intrigued when I was able to find this, is that for 4D bulk, actually the theory that I was reconstructing before, right? So CFT3 ADS4, you can find the sequence analytically, okay? So the QNs can be found analytically. It's very simple. So QN, where the mode passes through the Matsubara frequencies, goes as n to the 1/4, okay? So, and then I was sort of intrigued, is this, the natural question was, okay, fine, this function goes through an infinite sequence of points. Is this enough to reconstruct the function? And if it is, then, once you know the hydro function, then you can also reconstruct the rest. There's also an interesting question, why I was able to do only this in 4D and not in any other dimension. So actually, I don't have really time to go through this, but we have a new paper now with my student Mile Vrbica from Edinburgh, where we explain why actually this is the case. So there's something special about 4D gravity. And this, there's a long story associated to this, but basically what happens in 4D gravity is you can write the fluctuations, the linearized fluctuations. So linearized fluctuations have two channels. There's a sound channel and the shear channel. And by using something called Darboux transformations, same guy has nothing to do with the Darboux theorem from before. It's just a French mathematician who did many things. You can relate solutions from one channel to another channel, okay? What you can show is that, and this is sort of known before from the works of Chandrasekhar and other people later, but we used it now in the context of pole skipping. So what you can show is that, actually without pole skipping, for any solution in one channel, you can cook up a solution in the other channel with a linear operator L. And these linear operators in even and odd channels are, just some very, very, very simple operators, okay? Simple linear operators. And actually what we were able to do is to show that this is true for spherical flat hyperbolic black holes. Actually also doesn't matter if this is true in ADS, Minkowski, and DS. It's just always true that these relations are valid. Anyway, so what you can show for these pole skipping points in 4D is that essentially they fall into two categories. There are those which are historically associated with what is known as an algebraically special solution. Algebraically special solutions are those that have a zero kernel of this linearized operator. So the solution of the wave equation is annihilated by this operator, okay? This is very similar, by the way, to supersymmetric quantum mechanics, something like this. Anyway, I don't have time to go into this. So there's an infinite set of pole skipping points, which are algebraically special. They're annihilated by some operator. And everything else are common pole skipping points. So they're the same in the two channels, okay? So the even and odd channels have the same set of those infinite number of pole skipping points. The algebraically special ones are actually not the same in the two channels. This is actually the list. We find all of them analytically. And what is amazing is due to this special sort of integrable property of 4D gravity, you can find it analytically. So actually this result that I found before is a special case of these algebraically special solutions, okay? So we were able to show this. So this is 4D. And then the question is, well, let's say these pole skipping points, okay? So only the pole skipping points here through which the diffusive pole passes, okay? So this is unpublished work, so I'm not going to talk about it because, well, one is that I don't have time. The second one is that it's not published, it's coming out very soon. But the question that I was interested in is whether just this knowledge it's an essentially, it's an interpolation problem. So you know that the function goes through an infinite sequence of points. Is this sufficient in some way to reconstruct the whole thing? And it's conceptually quite nice because all of those positions, all of those points are computable, not from a differential equation in the bulk, but actually from an algebraic manipulation. And the most clear way of seeing this is by this determinant method that was developed by Richard and collaborators in this JHEP. So it's, it's a sequence of algebraic manipulations to get these QNs. And then the question is this enough to reconstruct the whole dispersion relation of Hydra mode? And then from that, using our previous work, one can claim that this is actually enough to reconstruct the entire spectrum. So what I would like to claim is that yes, the answer is yes. The way to do this is far from easy or obvious. It's actually very complicated. But the claim is that you can do this in principle in any dimension. Okay, so you can do it for n equals to 4 super Young mills, which is, d is equal to 4. You could do it for d is equal to 3, d is equal to 6, for the, I don't know, 2,0 theory, whatever this is, the M5 brains. So for these examples that are sort of similar enough to what I was discussing now, I would claim that this can be done. Okay, and since this is work in progress, I will talk more about this, I guess, at some other occasion. Okay, good. So let me just summarize. So I showed you a number of results. There are two main claims that I would like to make. So I first showed you how, there are various complex analytic structures associated to transport, which we've been looking at, and I guess many other people have also been looking at this. And I think, by now I believe that this is somehow useful, that we can learn quite a lot. So the first claim, is that in some QFTs, at least of the type that I was looking at, the reconstruction of the entire spectrum is possible, starting just from the infrared mode all the way to the ultraviolet. Actually, basically the knowledge of any of these modes is enough to reconstruct everything else, okay? It's an equivalent statement. So in momentum space, as I said, it's nice because we're dealing with convergent series, and we can do this very nicely. I guess you can also do it very nicely in position space, and then you have to use, methods of resurgence. So those, I think, reconstructions of, whatever people were calling them, instantons or whatever, I don't know. It's, kind of morally the same as the reconstruction of these gapped modes. In position space, it looks like an instanton. Because the series is non-convergent, there's some, it looks like a trans series, so it naturally looks like an instanton. But I think morally, it's the same kind of physics. It's reconstruction of some ultraviolet stuff from the infrared. So as I showed you, I think this is useful, actually, not only for QFTs, but because these are essentially the same problems, also for quasi-normal modes, just from the point of view of gravity. And also for other algebraic problems, for example, just in pure mathematics. I don't know, it's to be seen if this can actually be used for something there. So what is sort of, I would say, work in progress is to make this more practical, to make the reconstructions better, to maybe learn what is the most efficient way of doing things. Should it be Darboux? Should it be Darboux-Padé or Darboux-Padé? With some uniformization maps, it's to be seen what is the best, most efficient way to do this. And then, of course, the question is, can this be used for something, more realistic, like Euler-Heisenberg, chiral effective theories, things like this? Okay, so that's the first part of the talk. And then the second part of the talk was, telling you that there's some new structure in pole skipping that we uncovered for 3D CFTs. Why 3D CFTs? Because that was the actual example that I was also calculating before in this first part. And then, there's a sort of an open question of what one can do. Is there something like this in higher dimensions? Probably not. Actually, 4D gravity seems to be very special. So this was also known before. 4D gravity is very special, but maybe there's something, who knows? And then the last claim that I was trying to make, and that I didn't really substantiate, but it's kind of, to be determined and to be presented soon, is that I believe that the full reconstruction of the entire spectrum is possible from only knowing a single infinite discrete set of pole skipping points, okay? And it's particularly convenient for this set of pole skipping points to be the set that the mode, in this case, diffusive mode, passes through, okay? So then it's some kind of an interpolation problem, which we solve in some way, and then it's interpolation problems are tricky in general, but then once you have this, then the rest of the spectrum follows if the claim from the first part of the talk is true, okay? Which, I believe, at least for these types of theories that I was talking about, is true. Where it's true, what is the family of theories? Is it all to do with Hoyne? That's to be seen, okay? This is to be seen. Okay, thanks very much.
Thank you very much, Sašo, for a very inspiring and interesting talk. I have some questions, but I should also ask first in the audience, are there any questions? Well, maybe I'll ask my first question then. So while the audience is thinking, or maybe waiting for me to ask my question, in a sense, what you're telling us is that you can tell the convergence radius of the hydro approximation from just an expansion of the lowest mode, the quasi-normal mode, that is hydrodynamic.
Yeah, so I guess the convergence radius you could get anywhere. I mean, you could get that anyway, right? With any method on finding the convergence radius. What I'm saying is that you can find everything else as well from the coefficients.
I find that first part already remarkable, because that's right. That's really what is interesting, most interesting in the, I would say, in the real world, when you're dealing with hydrodynamic approximations to many body systems, and you're trying to understand what is the transport and where's the limitation of my description, of my hydrodynamic description. And then, like in any effective field theory, you would want to understand where that field theory breaks down. And and so in some effective field theories, you have methods that one can use, but here you're giving us like an answer to a question that people have raised several times regarding, like, for example, modeling the quark-gluon plasma hydrodynamically. You're saying you can determine the momentum where this breaks down, and therefore also the associated frequency at which this breaks down, this description.
Yeah. So these are very, these are sufficiently simple theories that you can just do everything explicitly. I mean, okay, maybe you still have to do it numerically, but yeah.
So these were all isolated excitations. So right. So now the real world theories have branch cuts and such. And so
maybe.
to what extent would this hinder the methods you've been working with? This is aiming at the like, making this more usable, like one of the points in your first box on your future directions.
Yeah. So it's a very good question. I mean, I would say that we don't actually know what the real world looks like from the point of view of correlation functions. So, I mean, okay, we know that at zero temperature, there's a branch cut. Even in these theories, at zero temperature, there's a branch cut. So the CFT has a branch cut at zero temperature. That starts at K. Well, yeah, okay. You know what I'm talking about. So there's a cut. In a zero temperature CFT, there's always, so we're talking about this structure. Yeah. So
coalescing quasi-normal mode points
there's a cut. Yeah, there's a cut here on the imaginary axis. Sorry, on the real axis. So
is that coming from the quasi-normal modes coalescing, or is that coming in from infinity? It's
no, you can understand this. So if you go to zero temperature, what happens is that these quasi-normal modes come higher, come together, and they sort of, so the poles come together, but there's always a zero in between. So it's like there's a sequence of pole zero, pole zero, pole zero. They come together, then eventually the residues of the poles go to zero. It's a nice sort of little limit of zeros and poles coming together. Poles, the residue is going to zero, and it just sort of straightens out to an analytic function that becomes a cut. Yeah. So there's a log. Well, it depends on the number of dimensions, but in 4D it's a log. Now, when you have a cut, I don't know I don't know how to do a reconstruction when there's a cut. That's the simple answer. However, I also don't think that we know that there are cuts at finite temperature in anything. So you have cuts when you have zero coupling. That is known. So when you have zero coupling, you have an infinite sequence of cuts. This is Hartnell-Kumar, very beautiful paper. And then when you have perturbation theory, then there's nothing. I don't think, I mean, we do various things. You can do kinetic theory, you can do relaxation time approximation. You can do one loop perturbative calculations. The problem is the perturbation expansion that I think never dissolves the cut. So you need some kind of resummation to dissolve the cut into poles. And this is not understood at all, actually, how this happens at finite temperature in any quantum field theory. This is not known. You know, you can do something like SYK and you see poles when you actually calculate it at any coupling. If you do holography, you do it at finite coupling, then you see poles. And what we have been able to see in the past is that when you go from infinite coupling towards zero coupling, things really look like they form a cut at zero coupling. But now for a generic QFT with a, I don't know, TOF coupling being 3.5, what is it really? Maybe it's a mix of cuts and poles. Maybe they're just poles. Maybe they're cuts. I mean, I don't think anyone can answer. I'm pretty sure there's no known answer to this. There's a lot of intuition. There's a lot of work. Not even, actually, maybe not even a lot of work. There's been some work. Yeah, there's some intuition, but we don't really have a concrete answer for this. And also, you know, for example, lattice isn't able to go to sufficiently high frequency or momentum to say anything about these correlators. At least I would claim that we don't know. I mean, this is I don't, you know, I guess making bold guesses. My bold guess is that they're just poles and that cuts are at finite temperature and the cuts are an artifact of perturbation theory. Mm-hmm. But I'm not sure. I'm not sure. My guesses are based on holographic examples, on SYK, on things that, you know, I've been able to see. Yeah, we're trying to do some of this now from the point of view of kinetic theory, from doing, you know, higher levels in the BBGKY hierarchy and seeing how this plays into that. So we're trying to do something. But yeah, this is a very long answer. Sorry.
No, thank you very much. That was a very, very good answer. I should ask if anybody else has questions. Are there questions? So there's a question in the chat that I will read. It says, thank you very much for the highly informative talk. An unrelated question to the specific direction of the talk. How did you and collaborators first come up with identifying the plane waves and chaos coefficients in the OTOX?
Plane waves and chaos. So there's, I guess he means pole skipping?
I suppose it's probably the exponential behavior, I'm guessing, in the OTOX.
No, I think it was so historically was that the calculation of the shock wave is a nonlinear calculation in perturbations, but it's also a solution to the linearized problem. So we were looking at, you know, what does this mean? So if you have a solution, it's because of those delta functions for experts. So how can it be that something is a nonlinear solution and a linear solution? And if it's a linear solution, then, you know, it's a perturbation of the metric. So if it's a linear solution, then it has to have something to do with hydro. So then we started looking at this and we found that indeed it looked like a hydro solution, but only in the sound channel, in the you know, spin zero sound channel of the perturbations. And basically, it all worked out at one very bizarre specialized momentum, which was purely imaginary. And then we looked at what happens to hydro around that point. And indeed, the hydro dispersion relation went through the Matsubara, which was the pole skipping point. And then we looked at the correlator, and the correlator looked weird because it was very nice everywhere except at the point. So then we determined that, well, nothing else could have happened from, just complex analysis. There's no other explanation for what we were observing than there being a zero. Well, in the first paper, there was, in the first paper, this paper with Konrad and Vincenzo, we just had a sort of cryptic footnote saying that the correlator, does something. And then in V2, we sort of clarified this point. Yeah, it had to be the residue going to zero or crossing with the zero. I don't know, it was a bit non-linear, I don't know. But it's basically from looking at the calculation of the shock wave and recognizing that it's just looks so much like a hydro calculation that it just cannot be a coincidence. It went from that. Mm-hmm. I don't know, I hope I'm answering the question. That's what I understood from the question.
Yeah, Mohammed Reza says thank you. So I think it answered, your answer was satisfying. Are there more questions? That at the moment does not seem to be the case. Anybody a last chance? Okay, if that's not the case, then there were already a lot of thanks in the chat for your talk, and I will also conclude with that. Thank you very much for a very interesting talk and for your answers. We will now end the recording. And
thank you. Thanks
see you all
everyone
next week.
Coming.